Right. So today we have multiple small topics that we're going to review, and all of them relate to moles. So I've broken down the mole concept into three sections. So this is the first one. The very first idea is what we have already seen: relative atomic mass. We discussed it on, I think, the third day when we started this session. That what exactly is a relative atomic mass? It is mass of an atom. And that's the interesting part, that this is mass of just the atom. It's not mass of ion, it's not mass of a molecule, just the atom itself. Compared with 1/12 of carbon 12 isotope. Now, the problem with this statement is that are you going to just talk about one atom of all the different isotopes that we have? Turns out that's not right, because, for example, you take any element, they have isotopes, they have different masses. So are we going to take just the mass of that? So that's why we don't say that. We say it is the average mass of natural or naturally occurring isotopes of an element. So instead of saying that, okay, this is just the atom itself, we are going to change it. We're going to say it is the naturally occurring isotope. So what that means is that now we are taking care of all the isotopes. So I'll give you an example. I have chlorine. There's two isotopes of chlorine. Both are 17 protons, but one is 35 mass and the other 37 mass. Now, if I say that I'm only going to consider this one, then I'm discounting this one, which is not right. So that's why if you're talking about chlorine and we want one value for chlorine, we should take care of all the naturally occurring isotopes that are there. There are artificial isotopes, but anybody can make them depending on if they have the right technology and skills. So that's why we don't consider those. So how does this work? We look at how common is this isotope in nature. We call that thing the abundance. So 75% of all chlorine that we find naturally is this one, and 25% of all chlorine that we find is this one. So now we can find the average mass. How does average mass work? It is exactly like how your exam scores work. You have three exams, for example. The MCQ paper, now depending on whether you're doing IGCSE or O levels, the number will be different. But let me just say that that's your paper one. There's the paper two for theory, and there's the paper four for ATP for O levels. For IGCSE, it's paper two, four, and six. Now, let's suppose in 1 year, they give 30% weightage to this one, 40% weightage to this one, and the remaining 30% weightage to this one. Now, this is the weightage for that paper. And let's say there is a student who gets 80% in this exam, 90% in this exam, but they were sick or something and they couldn't do well in this exam, so they got only 20%. Let's see if such a brilliant student who is getting 80% and 90%, but bad luck, are they able to get, what grade will they get? Now, again, Cambridge does other statistical methods as well. This is a very simple thing. So let's see, what will their actual score be? So score is going to be this and this multiplied. So it's going to be 80% times 30% and 90% times 40% and 20% times 30%. And then we're going to add everything up. Now, because it's percentage, you can divide by 100, but I just use the sign itself, so we don't really worry about that. Now when you do it, you will see that this student gets a score of 66% overall. And that is how you will measure the actual final score, which combines everything else. So this is the individual score for the different exams, and this is the total score that they get. This one exam messed up their whole situation. But that's exactly how we calculate the average. We take the abundance, which is like weightage, and then we multiply it by the mass, which is kind of like the score, that what is the score or what is the mass of this isotope. And we take that 35 and we multiply it with 75%. and we take 37 and we multiply by 25% and then add them both. And there you go. If you don't have percentage, let's say you have ratios, so you divide by the total ratios. If you have percentage, you divide by the 100, or you use the percentage sign. If you're using percentage sign, you don't need to divide by 100. But if the percentage sign wasn't there, I will divide by 100. Now, this will give me the overall value, which comes out to be 35.5. And that is the average mass of this atom, this element. So that is whether it's this one or this one, we can say the average is this one. And with the average, we don't need to worry about what isotope we have. We can just take this one and that will be fine. So for example, why is this useful? Let's say I had HCl. Now HCl has many isotopes in there. Hydrogen comes in hydrogen 1, hydrogen 2, and hydrogen 3. There's 3 isotopes of hydrogen. Chlorine comes in chlorine 35 and chlorine 37. Now let's see how many different combinations of HCl I can make. I can have, and I'm going to use a slot method for this one. So let's say my first slot is for hydrogen, second slot is for chlorine. I can have 1 and 35. That's a total mass of 36. I can have 1 and 37. That's a total mass of 38. Or I can have 235 and 237. So that will be 37 and 39. I can have 3 and 35. I can have 3 and 37. That will be 38 and 40. Now let's see how many different masses I can get. 37, 36, 37, 38, 39, 40. You see, this is repeating. So that means I can get 5 different values for their overall mass. Now, is that something that we would want to calculate every single time we are looking at an atom or a molecule? No, because this is just a simple molecule, just 2 atoms. Imagine if I had many, many different atoms. Imagine if I had like chlorine, carbon with CH3Cl. Now I have to take care of 3 different isotopes here, the different isotopes of carbon, which can be many, and then chlorine's 2 isotopes. And then I'll be like, okay, what's the total mass? It's going to be a nightmare to calculate each and every one separately. So what do we do? To calculate the total mass, which is called MR, which is what? Mass of mass of a molecule or formula unit or ion compared with 1/12 of carbon 12 isotope. Now I'm just going to take the average of each one and add it all up. So carbon's average from the periodic table is 12. Hydrogen's average from the periodic table is 1. So 3 times 1. Chlorine's average from the periodic table is 35.5. So there you go. I add everything up and that is how I get the average value. I don't need to calculate for each isotope separately. People have already done it for us. In the periodic table, there are 2 numbers. The bigger number is the AR. The smaller number is proton number. So with the AR of each one given, we can easily calculate the MR. Usually there's one question that can AR or Z be in decimal points? So for example, AR is 35.5 for chlorine. Can I have 35.14 as proton number or something? No, because proton number means that you have this many exact protons. We cannot have half a proton. Similarly, the mass number means how many exactly protons or neutrons you have. You can't have half or a fraction of that. That is why, because this is average, this can be in decimals because this takes care of the isotopes and their percentages. But the actual value of each one, that cannot be in decimal points or in fractions. Okay, so now we know the mass, and using that mass, we can figure out that, okay, we have MR, we can easily calculate MR using the AR. Now let's say I have a question that there is some MR of 70 for something. How many carbon atoms does it have? So let's say the formula for this thing is CnH2n. I want to see how many carbon atoms does this thing have, which also has MR of 70. So let's see. It has n carbon atoms. It has 2n hydrogen atoms. And if I add all of their mass up, I'll get 70. Now, let me just multiply n with 12. So 12 times n will give me the total mass from carbon atoms. And 2n times 1 will give me the mass of hydrogen atoms. So just 2n times 1. And that is a total 70. Let's see, 14n is equal to 70, n equals to 5. That means this molecule has C5H10. So you see that if I have MR, I can easily figure out how many atoms there are in that thing. But if I don't have that, I can easily figure out the MR if I have the formula itself. Now, does it help us, or how many different kinds of MR are there? So depending on the bonding that we have, we can give different names to the MR. So for example, if you have aluminum hydroxide, and let's say this is a special ion. Now this ion's MR will be called relative ionic mass. It will not be relative atomic mass. It will still be MR, but this is going to be relative ionic mass. So I can just calculate the same way. I have one aluminum, I have 4 hydroxides, which means I have 1 aluminum and 4 oxygen and 4 hydrogen. And then I calculate the values up, 27 plus 4 times 16 plus 4 times 1. And that gives me whatever the total is. Why didn't I take care of the negative here? Because negative means there's extra electron. Electrons have very small masses. I can just ignore it. Now, what if I don't have that? What if I have a molecule like C2H5Cl? Now, this is again MR, but this time we'll call it molecular mass. So this is ionic mass. This is molecular mass. But they're all relative to 1/12 carbon atom. And same method, 2 carbons, 5 hydrogens, 1 chlorine. I always try to list them first, because then I can plug in the values from from the periodic table. So 2 times 12 plus 5 times 1 plus 35.5 for chlorine. And there I get the total value. Now, what if something has ionic bonding? For example, this one. So this will be called relative formula mass. Formula mass tells us, the term tells us that this has ionic bonding. But the method is still the same. You have 2 aluminum, you have 3 oxygen. You just plug in the values for each one and then calculate it. Now, sometimes you'll get it in brackets. So for example, sometimes you might get, this thing, for example. So you just open the brackets up, or you keep it within the brackets, but keep them separate. So there's 2 ways of doing this. One method is you're like, and there's oxygen plus hydrogen. So I put the brackets in there and separated everything. The other method is I open the brackets up. So I'll be like 2 oxygens, 2 hydrogens. But no matter what you do, you can still find the MR in the correct value. Sometimes you might get something like this, where there is water attached to it. This water is called water of crystallization. And if you heat this thing up, this water will evaporate. But if you have the crystals of this thing, you need this water. So how do you calculate the mass using this? You just keep it in the mass. So 1 copper, 1 sulfur, 4 oxygen, 5 water, and there's 2 hydrogen and 1 oxygen in water. So notice that for water, I put a bracket times 5. So that's one way of doing this. Water, because it's a very common molecule, many students already remember that its MR is 18. So you can also just do 5 times 18. Examiner doesn't really care about your detailed working. They need to see one step of working and one markers for your final answer. So that's basically MR.